Hi, this is a short video introduction to EvalC3. EvalC3 is a set of Excel tools for exploring and evaluating complex causal configurations. EvalC3 is supported by this website, which provides detailed information on how to use it. This workflow diagram describes the sequence of steps involved in the use of EvalC3. Each step is described in detail by drop-down menus located immediately below the diagram. When you open EvalC3, you will see this Get Started worksheet. Before you start, pay attention to the checklist on the right. Then proceed to the first step by clicking on Input Data. Then click on Paste Data. If you have no data already on the clipboard, you are given the option of using an example dataset. For more information about this dataset, go to the website, click on Input Data, and then Datasets, and see the reference to Crook 2010. Here it is. There are 26 cases representing 26 countries in Africa. The outcome of interest is the percentage of members of parliament who are women, and there are 5 attributes of these countries that are potential predictors of that outcome. All the data here is binary. Some of it is binary because there are only 2 possibilities. For example, there are quotas for women or there are not quotas for women. But there are other attributes where numerical data has been dichotomized. Where women members are more than 32% of Parliament, this is coded as a 1, and where it is less, this is coded as 0. The next step is to click on Select Data. In this worksheet, each of the columns are automatically given a status, which can then be edited. There must be at least one ID column and one outcome column. Other columns can be assigned as attributes or ignore. This step exists because it may be the case that a dataset has multiple outcome measures and many attributes, some of which are more relevant to some outcomes and not to others. The next step is to click on Design and Evaluate. On this worksheet, there are 3 sections. On the left is a menu where we can manually design a predictive model. In the middle are performance measures for any prediction model that has been developed. On the right is a button to explore alternative and better performing models using different search algorithms. Here is an example of a manually designed model. I have simply selected an attribute I think might be a good predictor of a high proportion of members of Parliament being women, the presence of proportional voting. Then I have entered the value of 1, meaning that this attribute is present, using the drop-down menu in the status column. I have also selected women's status as being high. In the middle, we can see how well this model performs. Under the Evaluate heading, we see a 2x2 truth table known as a confusion matrix. TP stands for true positives, which are cases where the model attributes are present and the expected outcome is also present. Here there are 2 such cases. FP stands for false positives, which are cases where the model attributes are present, but where the expected outcome is absent. Fortunately, with our current model, there are no such cases. FN stands for false negatives, which are cases where the model attributes are not present, but where the outcome is present. Here there are 7 such cases. TN stands for true negatives, which are cases where the model attributes are not present and where the outcome is also not present. Here there are 17 such cases. Under the Performance Measures heading, we can see a range of measures describing the dataset we are using and the performance of the model we have designed. Each of these measures has an information balloon that can be clicked on to see an explanation of what the measure is all about. The overall group of measures tells us how well the prediction model performs. Accuracy is a measure of how well we have been able to minimize the false positives and the false negatives and to maximize the number of true positives and true negatives. Averaged accuracy is a better measure to use when the expected outcome is either uncommon or very common. The current model is not particularly good, having an accuracy of only 75%, but note that at the bottom we see a statement that the current model is not necessary, but it is sufficient for the outcome to be present. It does predict 2 true positives and there are no false positives. If there were no false negatives but some false positives, then the model would be necessary but not sufficient. If there were no false negatives or false positives, then the model would be necessary and sufficient for the outcome to be present. We could now go back and tweak our original model by selecting new attributes to see if we can improve its performance. Or we could go to the Explore section and click on Find New Models. This pop-up menu will then appear. We now have 3 automated search options. The first searches all possible combinations of attributes to find the best performing model. This works best for small datasets, but is very slow for large datasets. The second uses an evolutionary search process to find good performing models and is quicker when working with larger datasets. The third searches for the best performing single attribute and can then be repeated to find the best performing additional attribute that will improve that initial model. Regardless of which search option is chosen, a choice also needs to be made about which performance measure that will be used to evaluate the result of the search process, for example, accuracy. We can also impose constraints on the search process, for example, that false positives equal 0. In other words, we want models that are sufficient for the outcome. When we click on OK, the search process will go ahead, and after some time the best performing results will then appear in the Design menu and the Confusion matrix. Here you can see the results found by using the first search option and using no constraints. The best performing model was a combination of quotas being present and a post-conflict situation being present. This model had an overall accuracy of 88%. And note also that this combination of attributes was sufficient but not necessary for the outcome. There were 3 other cases where the outcome was present but not predicted by the model. The result of each automated search is automatically saved with a unique name, which can be seen here. We can view the details of all the saved models by clicking on View Models. A record is kept here of the attributes of each of the best performing models and how well it does on all performance measures. Any of these models can then be reloaded into the Design and Evaluate worksheet by selecting the appropriate row and clicking on Load Model. The last step in the workflow is to click on View Cases. This takes the currently loaded model and presents all the cases labeled according to the Confusion matrix categories that they belong to, and as sorted by ID number. Resorting by the status column will make the results more viewable. By clicking on Hamming Distance, a new column of data is added, which tells us which cases are most similar to each other in each of the 4 categories. A low Hamming Distance measure means a case has many similar attributes to other cases in the same category. This measure enables us to choose modal cases, those which are most representative, and to choose outlier cases, which are most dissimilar to others. Within-case analysis can then be carried out with such cases to find out what, if any, causal mechanisms are at work behind the associations that make up the model. Strategies for doing different within-case analyses are explained in more detail on the EvalC3 website. This process takes place outside of EvalC3, which is primarily designed to facilitate cross-case analysis. This has been a quick and basic introduction to EvalC3. For more detailed information on many of the options available, visit the EvalC3 website. Please note that EvalC3 is freely available under a Creative Commons Attribution Non-Commercial Share-alike International License.